Hey guys, here's a video to take you through how you set up the matrix that you need for your project. I realize that might be a little bit more confusing than average, so I want to spend a few minutes going through that. The first things first, I chose a picture that had roughly a polynomial shape. I want to remind you that polynomials tend to look kind of wavy, and anything that looks something like this, anything up from a parabola to a cubic graph to any number of bumps is going to be in the polynomial family. The one that I have has 1, 2, 3, 4 potential places that it could cross the x-axis, though. So this is a quartic function. It's going to be an x to the 4th type graph. I recommend you look at an x to the 4th or maybe an x to the 5th graph. Above that, it's going to get a little bit intense. The next thing I did was identify some points, and these are the points we're going to use to plug in for x and y. We're going to make a bunch of equations in order to solve for the unknowns, which are really those coefficients. So for general quartic, this is going to be y equals ax to the 4th plus bx to the 3rd plus cx squared plus dx and then plus e. And it's that a, b, c, d, and e that we need to solve for. So those are really the variables in what we're trying to solve here. Looking at how we begin to set up our system of equations, I'm going to plug in a couple points to show us what happens. First point I'm going to plug in is 1, 7. I actually lined up my picture in order to get 1, 7 on there because it's a nice clean number. I kind of wish I had made some of the other numbers clean, but that's what happens if you try to get them to be accurate to your graph, is that they don't actually come out nice. So when I plug this in, we get 7 is equal to a 1 to the 4th, which is 1, plus b 1 to the 3rd, plus c 1 squared, plus d times 1, and then plus e. So if you were to write this in standard form, this would look like 1a plus 1b plus 1c plus 1d plus 1e is equal to 7. That's going to be the first equation that we use in our matrix, and I'm going to show you how to do that in a minute. If I were to use a second point, let's just say this is 1.3 comma 7.6, we do the same thing. Y equals a times 1.3 to the 4th plus b times 1.3 to the 3rd plus c times 1.3 squared plus d times 1.3, and then that's plus e. And I should have plugged a y value in also. That's going to be 7.6. So in standard form, and I'm not going to do the math out for this, we'll see that in the next screen. This would look like whatever 1.3 to the 4th a plus 1.3 to the 3rd b plus 1.3 to the 3rd c plus 1.3 squared d. I went too many powers, so the c should have the square, the d should be to the 1st, and then plus 1e at the end. And this should equal 7.6. When you're making your matrix, this is going to be a matrix equation where you have a 5 by 5 matrix, you have a 5 by 1 matrix, that's going to be equal to another 5 by 1 matrix. The y values are going to go in your last matrix. So for the first 2 rows of mine, I'm going to have 7, and I'm going to have 7.6. The other 3 rows are going to be filled by my other equations. Your coefficient matrix is going to be built next, but let's throw those variables in there, a, b, c, d, e. Your first row for your coefficient matrix is going to be based on your first equation. In my case, that was looking at that equation where I plugged in 1 and had 7 at the end. So if we put this in, it's going to be 1 for the A, 1 for the B, 1 for the C, 1 for the D, 1 for the E. That lines up in my first row with the 7 in my matrix for the Y values. For my second row, I'm going to use my second calculated matrix. I meant to do that in highlighter. And that's going to look like this. 1.3 to the fourth, 1.3 to the third, 1.3 squared, 1.3, 1, and those should line up with your second number in your Y values matrix. You have to do the same thing for each of your other points. So we've got 1, 2, 3 other points for 1, 2, 3 other rows in my matrix. When you put these things together and multiply out those 1.3 to the fourth, to the third, squared, and so on, you end up getting something that looks like this. So if we go down to our matrix, we can now see where these numbers came from. My first row, 5 ones, goes with A and the 7. If I look at the second row, this is 1.3 to the fourth, 1.3 to the third, 1.3 squared, 1.3, and 1. Although I don't know why these are all 1.9. That's interesting. That would explain why some of my numbers didn't come out. That number is wrong. That should be 1.3 instead of 1.9. Here we used an online matrix calculator, and what we did was we took this and used this matrix.reshish.com thing. I inputted my matrix. I had to use a 5 by 5. And I'm going to use the inverse method for this. So we input the matrix into this setup here. You notice that again I had a 1.9, which should not be there, but that's okay. And what we did was we then solved this matrix, which gave us values for A, B, C, D, and E. And if you plug those numbers into an equation, it gives you something like this. From here, you can take your equation and go into Desmos, enter this with as much accuracy as you can. I used, I don't know, 6 decimal places. I probably didn't need to. But in doing that, it gave me as close to accurate as I could. I'm going to zoom out so you can see everything at once. And then finally, you take this and you compare this to your graph. I wonder if it's due to my using 1.9 instead of 1.3 that my graph didn't come out as well as I wanted it to. Or if it's just a matter of I needed more points here. If I did a polynomial graph that had an extra points all around Double the Dinosaur's nose, then this might have come out a little bit smoother. But as is, I think I hit those points pretty well.